Thank you very much. Thank you to the organizing committee for inviting us, and actually thank you to my colleague who's actually online. You know him, is Luca Rillo. He couldn't unfortunately join, so I'm here on behalf of Luca. And actually this presentation is four-handed and all the work is made by him, so I want to thank him also. So I'm Anna Testolin. I don't know if some of us already know me. As now I'm the technology manager of the circularity arena, which I'm going to talk you very briefly later on, which is actually bridging the gap and bringing us also to the eco-to-fuel and why we are working on that. So just a brief agenda of the presentation. We will just have a brief presentation of the Nora, very, very briefly, just to give you an idea of who we are and what we do. And then which is our approach in the partnership and collaboration, and so why we are working in eco-to-fuel, which is our role, the scope and the objectives of the task, and then some details on the scaling up of the MEA, which are the technical hurdles that we encounter, especially in the formulation of the ink and the electrode manufacturing, some test and characterization, and then the summary in the end. So the Nora, who we are an Italian multinational company. We are listed in the Euronext Milan Stock Exchange from actually 2022, so it's almost 4 years now. It was founded in 1923. So basically more than a century ago. I will just give you a brief idea of the timeline and our history. So it was founded in 1923. There was actually a century of electrochemistry from the DSA electrode on the market in the 60s, and then the diversification of DSA in the 80s. Some strategic acquisition in 2020 of Permelec, and then the joint venture with ThyssenKrupp in 2015. After that, we expanded our domain also in water technologies with the acquisition of STWP. And then we enter in 2017 in the energy transition era, thanks to some minority investment from Blackstone and then from Snam in 2021. The entering in the stock exchange, as I said, in 2022, and from that, I mean, our journey that is keep going. Some numbers, I'm not gonna say a lot of this, just to give you an idea of how we are dislocated all over the world with our manufacturing sites. Regarding the research centers, we do have one in Italy, that's the central one, but also in America, so the Nora Tech and the Nora Japan, we do have a couple of Fujisawa and Okayama. So basically every day we work with our colleagues in all sites. We do have projects that are shared, so it's a really close connection. As of 31st of December, we were 2,080 people. Those are the three areas in which we basically work. The huge one, that's the electrode technologies. So we are the world's largest supplier of high-performing coatings and electrodes for the industrial application. We are also active in the water technologies field. So we are provider of disinfection and filtration solution. And then we enter the energy transition. So we are trying to play a key role in the green hydrogen market. So our focus is also the sustainability. So that's our commitment, how we want to do so. We are actually working in the last year in this circularity arena. That's a strategic platform because we know that circularity is responding to multiple trends. So the trends toward the electrification, the need to answer the raw material scarcity, and also to reduce the CO2 impact. So how we want to work on this arena, we do have like three main areas. The first one is salt splitting, so working on lithium and other salt splitting. So that's one of the main area in which we are working. CO2, that's the electrochemical CO2 reduction into added value chemicals. So that's why the eco-to-fuel really fits. And also some starting work on CRM recycling. So the potential opportunity on lithium and other CRM recovery. Which is our approach. We know that sustainability and circularity requires innovative and collaborative approach. So we really believe in the partnership with university just to, let's say, bridge the gap. So we, as an industry, we really want to let's say, give to the university the possibility to go big, but do it properly, let's say. But also we do need, as industry, to work on more basic research, to do some research that maybe we also do not have time to do, because that's the problem of the industry. So that's why we really believe in the partnership, and that's why we work also, and we participate in the European R&D projects. So here we are, and that's the participation in the eco-to-fuel. As it has already been said, so I'm not going to repeat, but here in this graph you see where we are. So we are in the membrane electrode assemblies, and today I'm going to talk about our role in the project. We are the leader of the work package 5. That is the optimizing and scaling up of state-of-the-art electrodes and MEAs. So let's say we do have from intermediate to final target, working both on the electrode and then on the final sandwiches structure. So electrode, it was already shown before in the presentation. We are working on the GDE. The magic of the GDE, being able to work with the gas, a solid, and the liquid. So that's why we really need to structure this electrode, and then the final sandwiched structure, anode, cathode, and the membrane inside. I'm not gonna spend so much on this. It was already described. We know that scaling up has several technical hurdles, starting from the catalyst. This was already discussed from monolithos, but we have to keep in mind that a good catalyst, a lab scale, is not necessarily a manufacturable catalyst. We are going to focus in this presentation on the hurdles in the ink formulation and the electrode manufacturing. For example, for the ink formulation, we have to keep in mind that one ink, so one formulation, not necessarily fit all the electrode manufacturing process. So it really needs to be tailored to the application, working on the stability, on the rheology, on the solvent and the ionomer interaction, and also thinking about the scaling up mixing that can be high share, low share. So that's something we need to keep in mind. And also the electrode manufacturing. We will see that we are using two different way of manufacturing, the roll-to-roll in the case of the cathode and the spray coating in the case of the anode. And we will have a fully automated or a semi-automated production due to these differences. And we will see that the performances that are achieved at lab scale not always match what we are achieving in the industrial scale. So, example of what we did in the case of the anode ink. As I said, in the case of the anode deposition, we are using spray coating technique. So, of course, we do have as a substrate, in this case, it's a felt, it's a nickel felt from Vickert. And since we are spraying the catalyst on top of the felt, we need the evaporation to be fast. Otherwise, the substrate is going to be completely wet. So in this case, we needed to pass to an hydroalcoholic solution, not just a water-based solution, and that's effect. And also, we need to ensure that the ink is stable for for a proper amount of time, because if we think about the lab scale, that is the air gun, just doing a spray on a small area, we keep our ink stirring during the time of the deposition, we take an aliquot and spray, no problem. But if we are using the automatic spray coater, it's just the ink that stays there for the whole time of the deposition. So it really is necessary to be stable, otherwise we are getting a gradient of concentration and also clogging, because we have particles that are depositing. So that was the problem. So we need to work on a proper stabilizer in the formulation. And also we saw that we couldn't use like conventional binder that we normally use in our ink at the Nora. But what we did was to add the ionomer, it was already said in the before, in the ink formulation. So those help us both for the stability, but also with the ionic conductivity of the whole structure. And again, another parameter that we need to optimize is the speed and the height of the spray coater on the substrate. Here are some images of the electrode that we can make. Is 58 per 30 centimeter. We are depositing, in this case, the nickel iron LDH catalyst developed by CNR. And as I said before, in this case is a semi-automated production, because we can produce, the optimization of the parameters let us produce 4 electrodes per day. So that's, let's say, 5 if we really stretch our time, but no more. In order to increase the production rate, our site in Germany, the Nora Deutschland, purchased a new spray coater. So let's say we can double at least the production. But still, the production for the 1 megawatt stack has been started in IDN. More than 100 electrodes have been manufactured and ready to be shipped. And 30 more full-size anodes have been shipped to Vito for the 50 kilowatt stack assembly. So that was regarding the anode. As I said, the cathode, it's all another story, because in this case, we are using a different technique. That's the roll-to-roll production. We do this in our site in Germany, the Nora Deutschland. Something is okay. And also in this case, what we need to consider, starting from the lab to the industrial scale. In the case of the lab, what we normally do is using a brush. So that's what we do in the lab. And in this case, we really have, we can work on flexible ink formulation, because it's like operator dependent, the way we do the GDE. It's a low shear instead of the high shear in the case of the continuous process. And also in the case of the lab, it is possible to work both on sintered or not sintered GDEs, while in the case of the large area on the Cotima, that is the instrument that we use, it's possible to work only on no sintered substrate. So this is also playing a different role. And another important parameter is the oven that we are using. If we have a small area of the electrode, we can use like a lab oven in which we really have a controlled temperature. While in the case of the large area, we have industrial furnaces, like meter scales of furnaces, and we discovered that sometimes we can also encounter some problem in like temperature gradients. They can also be like tenths of grams, and this can play a crucial role in the final sintering process. So for the cathode side, again, the size is the same of the anode, of course. The catalyst is the copper oxide by UPV, and in this case it's a fully automated production. So we already finalized 2 scale up, the first one in October and the second one in March 2026. We will see later on the results of the 2 scaled up processes. here, as I said. So here we are comparing, let's see, the color is yellow, gray, and blue. Those three MEAs are the first one, the cathode is the first scaled up. The anode is always the same. In the second case, it's a lab-made cathode. And the third case, the blue one, is the second scaled up. So here, if we look at the results at 300 milliamps per square centimeter, which is the target of the project, it seems like the first scale-up is actually the best performing one, because we are getting the lowest potential. Also looking at the, let's say, the graph at the end of test. But then what could also happen in this case, it could happen that we are actually producing just hydrogen, and that's the problem of the cathode that we saw, because in this case, by looking at the contact angle of the GDE, we discovered that the back of the GDE side is completely hydrophilic. So actually, just at T0, so just at the start of the test, we are getting the electrolyte that is flooding the GDE. So it's basically just doing hydrogen. It's just getting water, and the only thing that it can do is hydrogen. So that was the problem that we encountered. So we saw that the key parameter that we need to modify is the hydrophobicity of the GDE, not only on the front side, but also on the back side. And so in the lab, we try to adjust some factors, some process, working on the sintering. So changing the temperature and the time of the sintering. So in this case, you clearly see that we were able to, from the contact angle, we see that also the backside is hydrophobic. And if we look at the GC analysis, we do have nice production of ethylene, just at also after 2 hours of test. We still have some hydrogen, but if we like sum the ethylene and the carbon monoxide, we are, let's say, over 60% production of gaseous carbonaceous product. So it's a very nice results. So we tried to reproduce this aspect in the industrial scaled. So doing this in the second scaled up. Still, here is the what I wanted to pass before as a message. So what we obtain in the lab is not always what we obtain at the industrial scale. So we were able to increase the performances. The hydrophobicity is reached, but again, we are not reaching the same results of the lab scale. I mean, it's still good because we do have nice production of ethylene and carbon monoxide, but still it's lower than the one obtained at the lab. So that's a starting point on which we want to work on. So regarding the sintering, we worked on the sintering, but also we are let's say planning to work on a different GDL structure in order to increase again the hydrophobicity of the GDL. So this is just a summary of what we saw. So the scaling up was successfully achieved. The cathode is a fully automated process, while the anode required a semi-automated one. We saw several technical hurdles, but I mean, we were able to tailor all these, the ink and the scaling up, and we saw that the key is the hydrophobicity of the GDE. And as a path forward, as I said, there's the investigation on different GDL. So we are going to use an alternative, the Nora commercial sample, as a GDE with an increased hydrophobicity of the MPL. And we are already planning a new scale up in mid-July 2026 in order to, let's say, see what we are getting as results. for this, I thank you for the attention. I thank the founded project for giving us the opportunity to work on this, and again, the organizing committee for inviting us.
Thank you, Anna, for the nice presentation. Is there any questions from the audience?
Thank you for your presentation. Well, generally speaking, when I participate in conferences and workshops, I'm dedicated to CO2 valorization and alternative and advanced processes for its conversion. And generally, I ask to myself, what is CO2? Because in my opinion, it's much easier to emit CO2 than changing CO2, converting CO2. So, in your opinion, what's about the economic and scientific impact of the pretreatment processes before applying, before using your technologies? Fantastic. Sure.
Okay, I'm not sure if I really got your question, but what we can say, yeah, let's say that the market of the CO2 is still quite. We see that I mean, it's not really clear. So for now, so that's why we are started working on this. That's why we are start working on this project to see whether we can make an impact with our technologies. I agree with you. I mean, it's easier getting CO2 in the ambient than starting working on that, but we need to start in some way. So that's my opinion. I don't know if I got your point. Maybe you are talking about what we can do before treating CO2. So that's the
We use CO2. The thing process or consider practical reality because generally CO2 is present with other gases. That's the process of coming from chemical base products. Therefore, the pretreatment aspect is
essential. Yeah.
So you are extending people of an industry. The question I am going to ask every time when people are involved with industries to develop something useful in their real life. So thank you.
No worries. Is there something there?
Yeah.
Okay. Sorry.
Here you have total fire efficiency greater than 100%. Like if we do some of the products.
Because the blue is the total. Yeah. No, I mean, yeah, I was looking now. This I said, okay, that's true, but no, that's the blue is the total. Yeah, no worries. I think there's something there. Yeah.
Okay, there is a few questions online, but I'll pick out only one or two.
Yeah.
Is it on? Yes, on. So thanks for the excellent presentation. How do you control the hydrophobicity on both sides of the GDE?
Yeah, that's the tricky part. I mean, that's what we are actually working on, trying to tailor the ionomer content in the ink, the sintering process, tailoring the temperature and the time we are using in order to give, let's say, the binder more time to melt in the solution in the GDE. But yeah, that's the tricky point in which we are working on. So that's the part we really need to focus.
You can mention the patent.
Yes, we already have a patent on this GDE that is basically explaining that. Yeah.
Yeah. So more specifically, not too many details can be
Yeah.
shared, right?
Yeah.
All the fabrication
Sorry.
process and conditions are used. Details cannot be shared. So another question, what ionomer do you add to the ink in the manufacturing of the cathode? The shredded hydrolyte membrane, question mark. Which membrane, question mark?
Yeah, that's all. I mean, that's all confidential information that we cannot share so much because the membrane and the ionomer that we put in the ink is from hydrolyte, while in the case of the Nora production of ink, we do use different kind of binders, but again, this is a part of confidential information that I cannot share too much. Yeah.
Yeah. Okay. What is the purpose of having high hydrophobicity on both sides of the GDE?
Yeah, that's what we saw before, because the hydrophilicity, it's really getting the GDE flooded. So in this case, we just have the electrolyte that is reaching the surface of the electrode. So the only thing that the electron can do, I mean, that really wants to do is hydrogen. So we are not converting any CO2 to carbonaceous fuel. It's just getting hydrogen.
Yeah, so just to add more onto it, we don't deliberately make the back of the GDE hydrophilic or hydrophilic.
Yes.
It during the process of fabrication,
Yeah.
it changes, and then we have to modify it in according to the application for CO2 electrolysis.